I did previous videos showing how you can take resistors both in series and in parallel and simplify the electric circuits by thinking of the equivalent resistance. And so I showed you how you can calculate the equivalent resistance of series resistors and equivalent resistance of parallel resistors. And so now I'm going to do the same thing with a capacitor, both a series of capacitors and capacitors in parallel. And so I've already got the circuits drawn. And in the first scenario, you have capacitors in series. Now, you're going to find the mathematical structure of the equivalent capacitance is going to be different for series and parallel than it is for resistors. But the very notion of whether something is in series or parallel, that remains the same. So in the first example you see in the upper left, those are two capacitors in series with each other. And by a capacitor, which is often defined as C, equal to the charge stored by the capacitor Q divided by the voltage across that capacitor. So you can think of a capacitor as two plates that are separated by some distance. And unless told otherwise, you can assume that there's a vacuum between the plates. However, different capacitors have different things in between the plates, which is often called dielectric material. And that dielectric material is going to determine the capacitance of that particular capacitor. And so you can imagine different dielectric materials is going to result in different capacitances. So when you have different capacitances at a given voltage applied across the two plates, you're going to be able to hold more or less charge. So in the first case scenario where we have in series, we'll call this capacitor C1 and we'll call this capacitor C2. And again, they're in series, and they're in series because there's different voltages when you first encounter C1 versus when you encounter C2. I'm also going to write C1 and C2 down here. Those are in parallel. Now, if you notice, in that case, the voltage drop across each of those capacitors is the same. And that's the definition of parallel, is that the circuit elements are subjected to the same voltage drop across them. So it's not the same voltage drop in the first case, that's series, it is in the second case. And I'm going to show you how you can simplify both of these circuits. So one thing to address here, you would think that like because the capacitor plates are separated, that the circuit would be disrupted. Like how does charge move about a circuit where you've got space between the wire essentially? And so what you need to remember is that when there's a potential difference supplied by an electromotive force like a battery, you have a plus and minus terminal. The plus terminal is of higher voltage than the negative terminal. And so if charge is supplied a path, it's going to try to flow from higher to lower potential. And so in this case, you got a current that's flowing in a clockwise direction. And so if you can imagine positive charges beginning at the positive terminal, they're going to start flowing. And what's going to happen is that those positive charges are going to pile up on this first plate. So you can think of that first place as having a pileup of positive charge Q. And so on the other plate, even though they're not touching, the electric field from the positive charges piling up very much gets to the other plate. And so remember, electric field is a hypothetical mass for if another charge is placed in that field, a force it would experience. So if you can imagine the electric field due to the buildup of the charge on that first plate, the charges in the second plate experiencing that field will experience a force that's going to want to move them further to the right. And so you can imagine that those charges keep moving until they build up on the second plate. And then similarly, the buildup of positive charge in the second plate has an electric field that's going to push positive charges away from that other plate underneath it. So the charges aren't actually going across the plates, but their buildup creates an electric field to push further charges down the line. And so if you can imagine when you have a buildup of positive charge on one plate driving away, because remember, like charges repel, driving away positive charges on the other plate, you have a deficit of positive charges, which is the same thing as saying you have a negative charge. And so then similarly, you have a deficit on this plate. So remember, we are in series. And so when you do a full loop of a circuit, that full loop has a potential difference that's precisely the potential difference that's supplied by the EMF, by the voltage source. And so I'm going to say that the total voltage supplied to this circuit is going to equal the voltage drop across the first capacitor plus the voltage drop across the second capacitor. Now, remember, capacitance is Q divided by V, and so I can rewrite this equation as V equals Q over C. Just some simple algebra there. And so that allows me to rewrite my voltage equation as Q over C, and I'm going to call this the equivalent capacitance, because what I'm ultimately going to do is show you how these capacitors in series can be thought of as a supercapacitor, i.e. an equivalent capacitor. And so then that's going to be equal to Q over C1 plus Q over C2. So I simply rewrote my capacitance equation so I could express voltage as charge divided by capacitance, and then I substituted it into my series equation where I know the total voltage is equal to the sum of the voltage drops. Notice that the Q is the same in each term because the total charge in the circuit is conserved. We're not interjecting more charge, or is charge leaving the circuit. So the total charge is conserved. And so what that means is that we have each of these terms canceling out. So you have 1 over your equivalent capacitance is equal to 1 over C1 plus 1 over C2. Now, like I did with resistors in parallel, because I hope you're seeing that this is actually starting to shape up a lot like our resistors in parallel, which is to say that capacitance in series has a mathematical structure for its equivalence that is the same as resistors in parallel. And so when I showed that derivation, I just did this little trick where I want to find a common denominator because I have 1 over C1 plus 1 over C2. They don't have a common denominator yet. So what I'm going to do is I'm going to multiply one term by C1 over C1. That's just a fancy way of multiplying by 1. And I'm going to multiply this term by C2 over C2, another fancy way of multiplying by 1. And so what that allows me to do is have a common denominator where I now have C1 plus C2 divided by C1, C2. You see how C1 and C2 is now my common denominator? And so if I want to figure out what the equivalent capacitance is, then I just take the reciprocal of both sides, which is to say that the equivalent capacitance is equal to C1, C2 over C1 plus C2. This has got the same mathematical structure as resistors in parallel. So resistors in parallel has a similar structure to capacitors in series. So I could rewrite my circuit as just a single equivalent capacitance. The charge is flowing like this, and I've got some equivalent capacitance, and that equivalent capacitance for resistors in series is given by the formula at the end of the arrow that I just drew. Okay, so now let's think about when we have the capacitors in parallel with each other. When the capacitors are in parallel with each other, they have the same voltage drop across them. So you can imagine that, again, we've got some charge in our circuit, and that charge is going to stay the same. It's going to be conserved. But when it gets to this point right here, it's got a decision. Does it want to go down across the first path, or does it want to keep going down this path? So the charge actually splits. Okay, this is called a junction. And so what happens is that you have some charge buildup, we'll call it Q1, on the first capacitor, and we have some charge buildup, we'll call it Q2 on the second capacitor. Now, that positive charge buildup is going to drive the charges on the other plate away. So you'll have a minus Q2, a minus Q1. But the key here is that the charge is conserved. So since the charge is conserved, we can say that the total charge is equal to the amount of charge that builds up on the first capacitor plus the amount of charge that builds up on the second capacitor. You'll see that that charge reunites when you get to the other sides of the capacitors. So capacitance, if you see at the very top in red, it's Q divided by V, but I could also yet again rewrite this equation where I can say that the charge is equal to C times V. So that's the capacitance in question and the voltage across that capacitance. Well, the voltage across both the capacitors in parallel is the same. So what I can say then is that I'm going to call this the equivalent capacitance times the total voltage is equal to the capacitance of the first capacitor. And again, they're all seeing the same voltage drop across them. So that's just a V again, plus whatever the capacitance of the second capacitor is in it, because it's in parallel, the first one also sees the same voltage drop V. And so now you've got the voltage terms canceling out, which is to say that the equivalent capacitance for these capacitors in series is equal to C1 plus C2. That should look familiar to when you have resistors in series, where you just add them together. And so now we can think of having a simpler circuit where we just have a single capacitor, where we think of the equivalence of the two original capacitors in parallel. And so now this term functions as the equivalent capacitance. Okay, so just remember, series means that you have different voltage drops across the circuit elements. Parallel means you have the same voltage drop across the circuit elements. You can, in all these cases, take more complicated circuits and simplify them by thinking about the equivalent resistance of the entire circuit. Now, with resistors, you just add the resistors that are in series together to get the equivalent resistance. That happens to be the same mathematical structure as capacitors in parallel. So resistors in series, add them together. Capacitors in parallel, add them together. Now, if resistors are in parallel or capacitors in series, you're instead going to use the equation where the equivalent resistance is equal to the multiplication of the capacitances divided by the sums of the capacitances. So the capacitors in series have the same mathematical structure for their equivalents as resistors in parallel.